Hey everybody. All right, this is chapter 7 and topic 7. So, we're only going to be doing 7.1, which is based on something called chemical equilibrium. Wow, that sounds like a mouthful to me. Is it going to be hard? Well, it's not easy, that's for sure. It really tells you certain ways of thinking. Because everything so far that we've been telling you, all the reaction that we've done so far is forward reaction, meaning that the reaction arrow points to the right all the time. But is it always like that? Nah. In fact, most reactions have the ability to go backwards, depending on the situation. And we'll see those situations today. Okay, because that's what equilibrium is about. Equilibrium known as balance. That's what it is. Okay, how our reaction balance from the forward reaction and the backward reaction. You'll be seeing that arrow a whole lot. So let's get right into it. Okay, in terms of the overview. The overview here is that we're going to be describing what is a chemical equilibrium. Okay, in a sense of what we know as dynamic equilibrium, linking to what we just finished learning, which is chemical kinetics, speed of reaction. We'll see what that means. Then we're going to look into something known as the equilibrium constant. Every equilibrium reaction has an equilibrium constant, which means it's a number. Okay, number that the reaction has to achieve in order for equilibrium to be established. We'll take a look at that later, I guess. Okay, so let's move on quickly. This is just an overview. These are things that you're going to be learning, sort of like learning goals. So today, we'll be spending most of our time right here. Okay, then we'll look at this the next day. Oh my goodness, there's so much math involved here. It's not even funny. And then part 3 of this lesson, we'll look at something called the Le Chatelier principle. And that's interesting. That's very interesting. So pay attention when we get there. So today, let's take a look at the overview. Dynamic equilibrium. So we talked about rates. Okay? And rates is defined as how fast the reaction is going. Or in other words, what is the speed of the reaction? Is it a very slow reaction or is it a very quick reaction? We graphed it. We were able to find the instantaneous speed at whatever point. We were looking at initial rate and average rate and stuff like that. That's all good. Okay? But how are we going to relate what we learned back in chapter 6 to now what we're learning in chapter 7? Well, this is exactly what you need to know. Is that in a reaction where you're going from A to B or going backwards, which we are going to replace with what we call an equilibrium arrow. Okay? That you have a certain speed for the forward reaction and a certain speed for a backward reaction, or the reverse reaction. Now notice I use this variable called K, which you're not going to see very much. K is called rate constant. That is not something that you need to know about, at least not yet. Okay, so what they're saying is that the rate of the forward reaction when at equilibrium will equal to the rate of the reverse reaction. So you're telling me that when you have a reaction where A becomes B, you mean that B can go back to give you A? The answer is yes, and it can happen anytime. In an equilibrium reaction, A is always making B, and simultaneously B is always making A. So when you make B, there is a chance that B could go back to A right away. So when the speed of the forward finally equals to the speed of the backward, that's when we say that this reaction has reached equilibrium. Okay? Pretty neat. Pretty neat if you think about it. But of course, this is something new. It is something that you're just going to have to get used to thinking, because most of the, right now, the idea of a reaction in your head is forward reaction, and you thought forward reaction only. But no, there are many, many, many reaction, that takes the advantage of going backwards. And we've seen an example like this before. We have. When we looked at acid and base last semester, I guess, we've seen that weak acids and weak base are based on equilibrium. What makes a weak acid and a weak base weak is because of its ability to go back, okay, to its pre-ionized form. That's why they're weak, because they don't create H+, at least not all the way, if you remember correctly. But that's what dynamic equilibrium means. These two graphs sort of shows, of course, where you have a reaction, okay, where you have H2 plus CO will give you CH4 plus H2O, some sort of reaction, okay? Where as the reaction proceeds, the amount of H2 and the amount of CO is decreasing, because these are reacting. They're turning it into HCH4 and water, while the amount of CH4 and H2O are increasing. So remember, in the beginning of the reaction, these products started off at 0 because the reaction haven't happened yet, man. And in the beginning, we have a certain amount of H2. We have a certain amount of CO. They're 3 and 1 respectively. So as this reaction proceeds forward, this is getting less and less and less. This is getting less and less and less, while these are getting more and more and more. However, there will be a point where they say, you know what? We're going to be stable. We're going to be stable, and we're going to be stable. We're not going to go lower anymore. We're not going to go lower anymore. We're not going to go higher anymore. This stability, where the lines plateau, is called, we're at equilibrium, boys. We're at equilibrium. We're not making more of these, and we're going to stop making these things go deeper down. If this was a forward reaction only, and not at equilibrium, let's change this. This is really confusing some of you, I think. If this was a forward reaction only, you'll see this go all the way to 0. Or one of these will go to 0. The one that is limited will go to 0. The one that is excess will stay at something. But these guys are going to go up. As you can see, that's not the case, isn't it? Both reactant did not go to 0. That means this reaction is an equilibrium reaction and not a standard one-sided reaction, if you know what I mean. Okay, here's the same graph, really showing you this time, instead of mass, we look at rates, that at a certain time, the forward reaction and the backward reaction are at the same rate, which is equilibrium. All right, let's continue. Okay, so there's certain points here that you kind of need to know. I wouldn't say memorize it, but try to understand it. That not all reactants are completely converted to products. We saw right here, okay, these reactants didn't all become product. They kind of plateau somewhere where they still have something. Why? Because it's a backward reaction that will replenish these at equilibrium. Okay? Reaction equilibria deals with the extent of the reaction. Oh, we'll see what that means later on. Okay, by extent of the reaction, obviously we're talking about other factors, like what happened when there's a temperature involved, what happened when pressure is involved, and what about catalysts? We talked about catalysts. How would that play? Arrows between reactants and product are separate. Okay, now we'll talk more about this. We're going to see this a little bit more, where we see that double arrow, which is an indication of an equilibrium reaction, whereas a single arrow is what we've been seeing all this time, which has no capability of going backwards. Okay, we know this already when we looked at dynamic equilibrium, that the forward and reverse reaction has to be the same in order for equilibrium to establish. Okay. So I have a little example right here where the rate of N2O4 decomposes the same rate as NO2 is being formed. At the same time, when this is being formed is equal to this being decomposed. Same idea. Okay. Now, this one is important. I would circle it. Okay, we're going to learn something called the Equilibrium principle later on in the third part of this lesson. Okay, and in order to see and collect data correctly, equilibrium reaction has to be done in a closed system. Now, what do you mean by closed system? Well, you have a reaction vessel where it is not being influenced or even disrupted by outside factor. Meaning that if you want to see what the equilibrium is for a particular reaction, you can't let more mass coming in, or you can't let mass in the reaction vessel escape, because when that happens, you're shifting the equilibrium. We'll see what that is later on when we take a look at Le Chatelier principle, okay? When a reaction is at equilibrium, the concentration, the pH, and the color remains the same. And that's when things kind of say, okay, let's stop here, because we have got it. We got into, we are in the goal. Oh, a whole bunch of points. All right, so here's some mathematical expression about, what we call rate constants. With this little variable here that I'm going to introduce you to right now is called the K constant, known as the equilibrium constant. That's what that is, an equilibrium constant for a particular reaction. And the reaction that we're seeing right here is N2O4. Now, don't worry about these equations because you don't need to know that, at least not you guys, okay? That the rate of the forward reaction is based on the concentration of the reactant, or the rate of the reverse reaction is based on the concentration of the product. You don't need to know that yet, okay? But what you do need to know is this, that the equilibrium constant is based or equal to the product of its coefficient divided by the reactant. Now let me write this equation, because I'm surprised that I did not write this equation. That you have N2O4 decomposing to give you NO2. Okay? First you have to balance this. Alright? If I say, when will the forward reaction equal to the speed of the backward reaction? Well, it will only equal when the concentration of the product to the power of its coefficient divided by the concentration of the reactant to its coefficient. All right? If the quotient of these equal to what the established Kc constant is going to be, we would say that this reaction has reached equilibrium. What that means is that every single equilibrium reaction will have a specific K value. And this K value, can be seen in many CRC handbook and your IB constant booklet. Okay, so in your IB constant booklet, there is a section where it shows you certain popular reaction and its equilibrium value. We're going to do a lot of math dealing with this, so don't you need to worry. Oh, look, I said it right here. Why did I have to do that right there? So at equilibrium, the ratio of the concentration equals at a certain constant, and that constant being Kc. So generally, a reaction like this has this as what we call the general equation of what we call Kc expression. Write that down. This is the equilibrium expression. All right. Hopefully you guys are okay so far. So let's take a look. There's an example on the next page, and let's take a look at that example. So writing equilibrium constant expression. For an aqueous reaction, the concentration of water do not appear in the equilibrium. Okay? Unless there's some sort of reminiscence about water that you really need to think about. But in most cases, when you see water, water is actually not part of your equilibrium expression. So make sure you memorize that. So if you were asked to write the Kc expression for this reaction right here, which is a very cool reaction because you're looking at an alcohol reacting with an organic acid to get something known as an ester. You will learn that very soon in organic chemistry. We are going to write out the Kc expression for this. So remember, is always the product to the power of its coefficient. So in this case, is the concentration of this guy. You're wondering what this is called. The name for this is called methylpropanoic. You're probably thinking, how did you know? I thought it was tricarbon, heptahydride, carbon, whatever. I give up. Organic naming, people, something what we're going to learn later on. So when you see this, this is actually called methylpropanoate. Don't worry, we don't know now. Well, this is divided by the concentration of methanol to the power of 1. Oh, there's the power of 1 here. Times propanoic acid to the power of 1. That is your expression. Notice that I did not write this down because this is equal to 1 at all times. Okay? Not 0. People say, but you scratch things out. Does that mean it's 0? No. If that's 0, you'll notice that your numerator and your Kc would be 0. That's absurd. Okay? So H2O is abbreviated by, of course, the concentration of 1. If the reaction takes place in a non-aqueous solution, water must be included. So this is when water, has to be included in your Kc expression. Okay? Is when you see that this is part of a non-aqueous situation. So it's almost like this. This is an example, but this is not a good example because it's not really an equilibrium expression. Actually, I'm not going to show you. It's not within your advantage to know anyway. But yeah, if you have a reaction that is not based on these aqueous, water is certainly part of a very important aspect of your Kc expression. So make sure you kind of memorize that. All right, let's take a look at the manipulation of the Kc expression. All right, and let's let's do a little bit of math. Let's actually put some numbers into these expression and make it a little bit more real. Put in some meat into this. So let's take a look at this part first. I have a reaction right here. And if I were to turn this into a Kc expression, it will look like this. Now, KCF, this means forward reaction. Okay, under the forward reaction, we have exactly what we know. Okay, the product to its coefficient divided by the reactant and its coefficient. Okay, what if I decided to flip this reaction around? Well, if you flip this reaction around, you're kind of seeing this as a reverse reaction. Hence, that's what the R stands for here, reverse. Then you'll have the other way where you have A and B being now the product in the numerator, and C and D now being the reactants in the denominator. And the relationship between KCF and KCR is the inverse of the other. Meaning that if you know what this number is, and let's say this is 5, okay, this is 5. If you're asked, then what would the equilibrium expression for the reverse reaction be? Well, it would be 1 over 5. Okay? So the reverse reaction is the reciprocal of the forward reaction, if you understand that mathematically. So let's take a look at this calculation. First, what they want you to do is there is a reaction involving water evaporating. The concentration at equilibrium, the water was 2 molar and 1.5 molar for liquid and gas respectively. So at equilibrium, when things are equal, the equilibrium, the concentration, of liquid is 2. The concentration of gas is 1.5. Calculate K. Let's do the Kc expression first. Always start with the Kc expression. So Kc expression for this reaction is H2O to the power of 1. Usually you don't even write that. To H2O liquid to the power of 1. And we know what those numbers are because at equilibrium they said H2O gas is 1.5 and H2O water is 2. Divide the 2, Kc is 0.75, and there's no units for Kc because Kc is sort of like a ratio. It is a ratio, so there's really no units for a ratio because it's not really a measurement, is it? Now, what is the Kc for the reverse reaction based on the same data? So at equilibrium, I want to know what is the Kc for reverse. So that means I want H2O liquid on top and H2O gas at the bottom if I were to look at this reaction reversely. Okay? That is no big deal. 2 molar divided by 1.5 molar, which is equal to 1.33 molar. Okay? Do we have to go through that much trouble to get 1.33? No, of course not, because we know that the reverse reaction is just the reciprocal of the forward reaction. So if we know that the forward reaction is 0.75, the reverse reaction in this case is just 1 over 0.75. You divide that, 1.33. Pretty neat. Okay, it's pretty neat to know. So if somebody were to give you the forward reaction of something, but they didn't give you any of these number, don't freak out. All you have to know is that to find the reverse equilibrium expression, you just take the reciprocal of the forward expression. Next page. Okay. Here's another one. This one deals with changing the coefficient. How will that work? So let's do these. Question 1. Determine the equilibrium constant for the formation of HI. If the equilibrium concentration, so at equilibrium, when things are cool, that Kf is equal to the rate of forward equals the rate of backwards, H2, I2, and HI are these molar respectively. So at equilibrium, so look at the language here. If the speed of the forward reaction is equal to the speed of the backward reaction, this is the concentration. What is Kc? All right, just like before, let's do the Kc expression. So the Kc expression in this case is Hi to the power of 2. Oh, look, see? Over H2 to the power of 1 times I2 to the power of 1. Hey, let's plug in those numbers. Okay, Hi is 0.189, in this case square, divided by H2, which is 0.006 times 0.106. I really should be putting units down. The answer is 56. Okay, the answer is 56. Okay, good. Let's take a look at question 2. Question 2 is the same reaction as question 1. The only difference is the coefficient. As you can see, the coefficient of H2, I2, and HI, which is really the whole system, is cut by half. 2 became 1. 1 became half. 1 became half. So you cut the coefficient by half. So at equilibrium, what would it be if you did that? Well, let's do this. Kc is equal to, in this case, Hi over H2 to the power of a half, which is really squaring it, times I2 to the power of half, which is, again, really squaring it. So let's put these numbers down, okay? We use the same number. The reason why you use the same number is because there shouldn't be any difference, okay, in terms of concentration. Concentration should remain the same in an equilibrium expression, okay? But then, of course, the equilibrium constant in this case will change. So let's plug this in. So in this case, this is 0.189 divided by 0.006 to the power of a half times 0.106 to the power of a half. What will that equal to? It would equal to 7.48. Something is cool here. Something is really cool here. If we were to decrease the amount of moles by half, it looks like my equilibrium constant, it seems my equilibrium constant is decreased by squaring it. Check this out. Kc is actually equal to the square root of 56. Because if you do that, you'll also get 7.48. So if you divide things by half, you will root. Oh, better not do that here. You will root when the original, I guess. Now, what if you do this? What if you decrease everything by 1/3? In this case, okay, this will be 2/3, 1/3, 1/3. What do? Well, if by a half you do this, if it's 1/3, you do this, which is cube root. If you decrease things by 1/4, same idea. Your new Kc will be to the quarter. Or in this case, fourth group. Fourth root. Doesn't this look so ugly? How ugly does this look? All right. So we sort of know two relationship, which I kind of summed right here. I summed it up right here. Okay, that when you have a certain equilibrium constant K and you reverse the reaction, it will be the reciprocal. If you take away half of the coefficient, you'll square root it. Or if it's you break it into thirds, you'll cube root it. This one I did not illustrate, but it's pretty obvious. What happens if I double the coefficient? Well, you square it. Let me show you what I mean. Let me show you. So instead of saying, 1, 1, 2, I said 2, 2, 4. How would KC change? Very simple. 56 squared. Okay. What if it's 3, 3, 6? So as you can see, I went up by 3 times the coefficient. 56 cubed. Same thing. Okay. Doubling the coefficient, square it. Triple the coefficient, cube it. Cube it. All right. I have 4 questions right here. Okay, I have 4 questions right here. I want you to do them. Don't think that only happened on one aspect. It can actually happen in 2 aspects, like this one. Check out this one. Okay, what is Kc for this reaction? If this is what it is normally. So if this reaction gives you 56, what would this reaction be? It looks like it flipped. So you're going to have to take the reciprocal. It looks like it doubled. So you have to square. So if I were to do this, Kc will now equal to 1 over 56 squared. Why? Why 1 over? Because the reaction is reverse. Why squaring 56? Is because all the coefficient is double from the original. Okay? So try these and we'll take it up the next day and see how you flare in terms of how, if you understand how all of this works. All right. Let's take a look at this, and then we'll call it for the day, okay? This is called reaction sequences. We see something like this when we looked at thermodynamics. When we looked at Hess's law. Well, some reaction is not a one-step reaction, but a stepwise reaction. So if it's a stepwise reaction, that means there are going to be various side equations. So let's say you have this equation right here. A plus B will give you E plus F. This is not a one-step reaction. No. In order for this reaction to occur, it has to make C and D first. So A plus B will give you C plus D. This C plus D will go through the next reaction to give you E plus F. This is actually a good example for biology because if you know cellular respiration, the first part of cellular respiration is glycolysis. This is very similar to glycolysis. Very, very similar, where the reaction is acting as a pathway of reaction. And they are actually equilibrium expressed. Now go impress your biology teacher. So if this is the step 1 of the reaction, obviously this can give you an expression known as Kc1 or just K1. If this is the second equilibrium reaction, we can actually call this Kc2 or K2. If this is the overall expression, all you have to do is take K1 and you multiply it to K2 to get your K3, which is your ultimate reaction. If this is the expression of Kc, it is actually equal to these two reactions, these two K as a product. And you'll notice that certain things will cross out, right? Now this is equal to that, see? proved it already. So I have an example here. Okay, I have an example here. I have this reaction. Your chalk reacting with carbon as a gas. Oh, that's interesting. To give you calcium oxide and carbon dioxide. This is not a one-step reaction. This is actually pretty difficult to accomplish in the lab. It's a stepwise reaction. It composed of two equations actually, to get this going. First, you have the decomposition of calcium carbonate. Then you have, of course, carbon reacting with the carbon dioxide to give you the carbon monoxide that you wanted. Okay, so it takes two reactions to get this. Well, this reaction right here has a K1 value of 0.039. So when the speed of the forward equal to the speed of backward, the expression will give you this as an answer. Same with this. For the second reaction, when the speed of the forward equal to the speed of the backward, it will give you a K expression of 1.9. So what is Kc for this? Just like what I said earlier. Multiply the two numbers together. Kc is equal to 0.0741. So, summarizing what we learned today, of course, we learned about the dynamic equilibrium, how speed is what dictates the equilibrium constant K. We learned that if you know the K of the forward reaction, you can easily find out the K for the reverse reaction. If you play around with a coefficient, you can easily find a new K value by doing certain mathematical work. If you're looking at a stepwise reaction, all you have to do is find the product of the K's. All right. Next class is a big problem. Okay? Mathematically, it can be very troublesome. We're going to actually look into if we have an equilibrium expression. If we have Kc, because remember, these numbers are all discovered for you and is in the handbook. Given this, are you able to tell me at equilibrium, what are the concentration of your entities? Let me say that again. If I give you the equilibrium constant, if I give you this number, can you tell me at equilibrium what these guys are? That's interesting. And we'll see you tomorrow. All right. I'll see you guys later. Bye.